Hello. In this video, we are going to look at some aspects of using the Z transform. Okay, we are first going to look at how to sketch DTFT from Z transforms. Okay, let's not say that from pole zero plots. Okay, and then we will also look at some connections between, let's say, if pole zero plots or let's say poles and zeros and magnetic response. Then we will finally look at minimum phase systems. Okay, so these are some things which we are going to look at as part of these lectures. Okay, let's first move to a blue color. Now, the first thing you have to realize when you talk about the pole zero plot is that the pole zero plot consists of the real part of Z and the imaginary part of Z, and you basically, of course, you can draw the unit circle if you want. It's useful to have the unit circle. I think select it and move it a little bit so that it's centered. Okay, so this is the unit circle, even though I am not marking it thus. And once you have the pole zero plot, then you can mark your poles and zeros. Poles are always marked with a cross, and the zeros are marked with a zero. Okay, naturally, this is the unit circle, and unit circle has to be within the region of convergence if you wish to have the DTFT. And of course, there is also connection with stability. Let us actually work on sketching the DTFT if you know the sketching the DTFT if you know the pole zero plot. Now, one important thing with the pole zero plot is you must realize that the pole zero plot has an extra scaling factor, because the pole zero plot essentially does this. Suppose you have something like 1 by 1 minus AZ inverse, then this tells you that there's a pole at Z. Okay, so let us actually consider something simple to begin with. 1 upon 1 minus 0.8 Z inverse. So we know that what this is going to look like. We know that the DTFT of this is going to look like something which is, so if you look at, if you know that you can basically just substitute 1 upon 1 minus 0.8 e power minus j omega, and you know that when you put omega equal to 0, this becomes 1 by 1 minus 0.8, which is 5, and when omega is pi, this becomes 1 upon 1 plus 1.8, which is 1 upon 1.8. So, but if you look at the pole zero plot, this x is the location of the pole at 0.8. So now, if you want to look at the magnitude of the DTFT, it is actually not that difficult. The DTFT, if you recall, is obtained by substituting Z is equal to e power j omega, which means that if you consider any point over here, you connect it over here, then this angle measured in this direction will be omega. Therefore, to obtain the magnitude response, here is one way to do it. You take, let's say I will call this h of z, you take h of z, and if you substitute at z is equal to e power j omega, you put a magnitude and evaluate it at z is equal to e power j omega, that works out to magnitude of 1. So 1 upon the magnitude of 1 minus 0.8 e power minus j omega. Now notice that this is also equal to 1 upon, because e power minus j omega has magnitude 1, I will write this e power j omega minus 0.8, which means this is the point on the unit circle, which is this point, and this minus 0.8. Therefore, let me choose a different color. In essence, this distance, this distance directly translate to the denominator, right? Because e power minus j omega minus 0.8 is the difference between e power minus j omega and the complex number 0.8. Of course, a real number. That distance is the denominator. Now that distance is actually minimum over here, and that distance is maximum over here. Which means if you want to sketch the magnitude response, it is going to be really easy. Okay, so we know that if you write h of e power j omega, then you know that when omega equal to 0, that is when the denominator is the minimum. It is at 0.2. So in fact, you can say it's at 5. And when omega is equal to pi, then the denominator is 1 by 1.8. So it is over here. Now over here, what happens? All you need to do is you need to basically measure this distance, this distance, this distance, and keep measuring those distances, and then doing the reciprocal and then plotting it, which is how you will get. So I'll say this is minus pi, this is pi, and the magnitude response is going to be something like, okay, that was very badly drawn. Going to be symmetric, but it's going to look like this. To prove it to you, I have my tool open. So 1 minus 0.8 and you see that this is exactly what it looks like. Of course, there's the minor issue that this is a log plot, which is why you won't exactly see it, but it makes complete sense. This is exactly what it is. So this actually plots 20 log, which means that the peak, which I told you is 5, which could be the log of 25. So the log of 25, if you know how to calculate, if you know how to convert to dB. So whenever you have 25, then conversion to dB will result in, it's I think 100 upon 4. So you'll have roughly 16 dB, which is exactly what it is. Similarly, over here it's 1 upon 1.8, which is roughly close to half, which is why you're going to have something like minus 3 dB or so. That explains it. Sorry, minus 6 dB because 1 upon half square. So that's exactly what it is. Similarly, we can also have a look at the phase response. Now, what is the phase response? Again, if you look at the angle of h of e power j omega, that is going to be, so if you look at the denominator, we are just going to take negative of angle of e power j omega minus 0.8. This is what it is. So we need to just find the angle made by, okay, this is e power j omega, this is minus 0.8. So we need to find this particular angle. Okay, e power j omega minus 0.8. So this is, okay, if you consider it like vectors, e power j omega is like this vector and 0.8 is this vector. You take the vector difference, then you're going to get this. Okay, so again, I'll repeat what I'm saying. If you say e power j omega minus 0.8, e power j omega is this point. So this is a vector e power j omega. Minus 0.8 is this is this vector. If you take the vector difference, then it's just, you basically just have this, and to this you have to add the negative of this vector, so that vector will be over here. You're basically going to end up getting this line, and this line is going to yield this particular angle, and we have to take the negative. We just have to take the negative of this angle. So let's find out how this angle varies. When omega is 0, this angle is 0. That makes sense. When omega is pi, what happens to this angle? Even then this angle becomes 0. In between, it traces all possible negative values. So you can basically, for example, let's do it at this particular location. At this particular location, this particular value is omega equal to pi by 2, which means this point is j. So we need to look at j minus 0.8. This is j, this is 0.8. So let me choose a different color. Let's say I'll draw it using green. So we need to take the negative of this angle. Okay. So j minus 0.8 is very easy. We just need to take So if you look at it, it's tan inverse of minus 0.8. Tan inverse of minus 0.8. Let us find out what happens if you try to compute the um, magnitude response. So let's take a point on the unit circle. I use red. Okay. Sorry. Okay. So then this becomes this is z is equal to e power j omega. Okay. What will be interesting is for us to find the ratio of the numerator and the denominator. So I'm basically going to convert this to magnitude e power j omega minus 0. Sorry. This is going to become e power minus j omega minus 0.2 upon 1 minus 0.2 e power j omega minus j omega. Okay, you know our trick of multiplying by e power j omega on both the numerator and denominator is going to be magnitude. I'll take the point 2 out. So let me do it carefully. This is going to be 5 minus 0.2. Okay, divided by what e power j omega minus 1. Now, how did I get this? See, notice that whenever you have this kind of situation, you can always take the conjugate and you can write this as, e power j omega minus 5, 5 minus e power j omega, doesn't matter. You can take the point 2 out common, you can prove that you get this. So the ratio is just the ratio of this line to this line. Okay, let us find this out. Okay, let us this should be 0.1. Okay, let us find this out. Okay, let us find this out. This point is actually cos omega, sine omega, and we need to find the ratio of these two, which it's not difficult for us to find out. We can basically see that over here this is equal to. We should not run this. I'm sorry. So I'm just going to say this is. It's going to multiply by e power j omega both sides. So this is going to become 1 minus 0.2 e power j omega, and I'm going to use the fact that the conjugate is the same. So 1 minus 0.2 e power j omega. Okay, that works out to 1. Okay, so in fact it works out to 1. But there's a slight issue. Over here, if you see, it seems that this 5 is much farther and this ratio is not exactly 1. Okay, why is this the case? Let's actually do the maths over here. What is the distance between this point and 5? It's actually the root of 5 minus cos omega, the whole square, plus sine square omega, which is equal to root of 25 minus 10 cos omega plus cos square omega plus sine square omega is 1. Let's find this distance. So this distance will be root of cos omega minus 0.2 the whole square plus sine square omega. Okay, now this is equal to, if you look at cos omega minus 0.2 the whole square and stand carefully, you get 0.04 minus 0.4 cos omega, and you get plus 1. So this works out to 1.04 minus 0.4 cos omega, and this works out to 26 minus 10 cos omega. So is there any comparison? Let's actually play a trick. So let me multiply whatever is inside carefully. So notice that I want to compare 26 and 1.04. 26 and 1.04. I think 26 fours are 104. So if I want to get 26 inside, then I need to divide by 4 and multiply by 100. So I need to divide by 4. Let me do that. We divide by and multiply by 4. So I'm going to get 0.26 minus 0.1 cos omega. So inside I've divided by 4, so I'm just going to multiply by 2 outside. Okay. Now to make up for this extra bit, I'm just going to divide and multiply by 10. So I'm going to get 1 upon 5 root of 26 minus 10 cos omega. So you can see that these two terms are the same and the ratio is 5. So why does this anomaly occur? This anomaly occurs because the pole zero diagram does not capture the fact that this numerator has an extra constant term or something. See, basically if I were to write it in the standard form, this would be minus 0.2, 1 minus 5z inverse. Right? Now that is this 0.2 extra appears as 1 by 5 over here. That's why this is happening. So this is actually a special type of system. This is called the so-called all-pass system because, interestingly, the omega does not the magnitude response does not depend on omega. It is constant throughout. Now, all-pass filters are special filters which have the property that they only alter the phase and do not alter the magnitude response. So think of it in this way: when you have multiple sinusoids, all they do is they just rearrange the phases of those sinusoids and add them back up. They do not alter the amplitudes of the sinusoids. This also can result in some modification of the waveforms, as you can see when you experiment till you determine it. But yes, all pass filters are really useful and occur in multiple situations whenever you have to deal with, say, some kinds of processing of audio and various other things. So I've done some simple examples. Let me do one final example which has multiple conjugate poles. So for example, let's say we have the system like this. Let's say that these poles are at 1 plus j upon root 2 and 1 minus j upon root 2. Okay, so this is where the poles are. So this is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Now, if you want to sketch the magnitude response, how will it look like? Well, if you are over here, then this will contribute a high amplitude to the magnitude response. This will contribute a little bit less. If you're over here, these two will contribute a little more. If you're here, it's the same. So let's find out what happens over here. This is actually z is equal to e power j pi by 4. At z is equal to e power j pi by 4, actually I should have made a slight change over here. Let's say I am going to call this 1 plus j by 2 and 1 minus j by 2. Yes. Okay. And what is the z transform that this corresponds to? It's this kind of all pole system, 1 minus 1 plus j by 2 z inverse 1 plus 1 minus j by 2 z inverse. Let's actually expand this out and see what we get. So that corresponds to 1 upon, so if you do this carefully, you get 1 minus, and 1 plus j plus 1 minus j will give you 2. So 1 minus z inverse plus, and 1 plus j into 1 minus j is 2, and divide by 4, so you get half z power minus 2. So this kind of all pole system. So let's evaluate what this is at z is equal to 1, which is what z is equal to omega equal to 0 corresponds to. So at omega equal to 0, this becomes 1 upon 1 minus 1 plus half, which is equal to 2. Similarly, the other salient point is at omega equal to pi by 4. So at omega equal to pi by 4, we get 1 upon, now we have to do this carefully, this is 1 minus 1, so z inverse, so 1 minus j, I'll write 1 plus j upon root 2 plus half 1 plus j the whole square by 2. Okay, we can evaluate this carefully. Okay, and otherwise we can actually just okay, let me evaluate it carefully, or rather let me put it over here. I can put it over here, so I get 1 upon 1 minus 1 plus j into 1 plus j upon 2 root 2, and the other one is going to be 1 plus 1 minus j into 1 plus j upon 2 root 2. Let's evaluate this. This is 1 upon 1 minus, and 1 plus j the whole square is actually 1 minus 1 plus 2j. So it's going to be 2j, which is j upon root 2, and this is going to be give me 1 plus j into 1 minus j is actually going to be 2, so 1 by root 2. So this number, if you take the magnitude, is going to give me, so this particular quantity is actually 1 plus 1 by root 2. So the magnitude is going to be 1 plus 1 upon root 2 multiplied by root of, I think this is going to give me 1 plus half root of 3 upon 2. Okay, so now the question is whether this number is more or less than 2. Okay, so that is something which we can just calculate very easily. So this is actually going to be 1 by root 3 upon root 2 plus root 3 upon 2. Okay, so this is going to give me, the magnitude is going to be equal to, so 1 upon root 3 upon root 2, 1 plus by root 2. Okay, now you can compute this. This is going to be roughly 1.7 root of 1.5. I think we'll just use a calculator and do it easily. Okay, okay, 3. So now I'm just going to plug pi by 4 into this particular expression. So z is equal to, so I'll just do import pi by p. Z is equal to np dot exp 1j to np dot pi upon 4. And if I now plug in 1 upon 1 minus, so I'll just do 1 by 1 minus z inverse plus 0.5 by z upon z. Okay, that gives me this number. I do np dot abs of this, I get 2.787, and if I now substitute z is equal to 0, sorry, I get a divide by 0. Yes, that's a problem. If I put z is equal to, oh, I should have put z is equal to 1, I'm sorry. That's 2. So therefore 2.78 means that when it comes to this pole, the magnitude is higher, which means that if you now want to sketch the DTFT, you're going to get something like this. You're going to get a peak, you're going to get something like this, and then it will fall. Okay, now the reason why it peaks here and falls here is because this distance, these two distances do not contribute enough. And similarly, you can see that at pi, it is going to have a very small value because you are very far from both of these poles. Let's actually check in our example. Okay. Okay. So now let's take a situation where we want to look at the DTFTs of systems which have same DTFTs. Over here, I've chosen A and B to be real deliberately, and I've chosen B to be larger than 1. So this is a system which has something like 1 minus bz inverse by 1 minus az inverse. Okay, so then let's actually look at the DTFT of this. So I'll call this h of z. So if you have h of z is this, then h of e power j omega, which mod h of e power j omega is actually going to be mod 1 minus b e power minus j omega by mod 1 minus a e power minus j omega. Okay, but let me play a trick over here. I can write this as e power j omega minus b upon e power j omega minus a, and I can take conjugates inside. So I'll write e power minus j omega minus b by e power minus j omega minus a. By the way, needless to say, because I am assuming that the DTFT exists, the ROC is going to be mod z greater than a. So now let us look at e power minus j omega minus b, e power minus j omega minus a. Okay, so now this means if I consider the alternate system, okay, z inverse, I'll choose a different color, z inverse minus b upon z inverse minus a. what does this system have? This system has a 0 at 1 upon b, and has a 0 at 1 upon b, write a 0 at 1 upon b, and has a pole at 1 upon a. So it has a pole somewhere over here, say 1 upon a. So this has a pole and 0 which are switched. Now naturally, since we want the DTFT, we have mod z less than 1 by a. Okay. Now this system can be simplified. Okay, let's take a particular example. I'm going to take something like 1 minus 3z inverse by 1 minus half z inverse, because I chose b to be larger than 1. So the reverse system will be over here. It is going to be z inverse minus 3 by z inverse minus half. Now if I want to carefully just pull this and bring it to the same form, it is going to be minus 3 1 minus 1 by 3 z inverse upon minus half into 1 minus 2 z inverse. Now since I am going to do it, since I am going to basically bring it to that side, is going to be 6 minus 2 z inverse by 1 minus 2 z inverse. I think that is something which we can quickly try. So 6 minus 2, 1 minus 2. Let's try to see what this is. Okay, yes. So indeed this seems to, the reason this happens is because it seems to blow up on the right. Okay, that tends to happen. But there is a well-defined magnitude response. We'll have a look at that in a minute. And then if we compare it with the original system, which was 1 minus 3z inverse and 1 minus half. So 1 is 3 and 0.5. Notice that the magnitude response doesn't change. The magnitude response remains the same. Except that the system changes, the magnitude response doesn't change. That is key to what this is. So this means that there are multiple systems that have the same DTFT. But what is the difference? So whenever there is a 0, at let's say b, if you make it a 0 at 1 upon b, or when you have a pole at a, make it a pole at 1 upon a, automatically that means that the magnitude response does not change. Can we make this more systematic? Well, if you look at this particular transformation, h of z, okay, has zeros and poles. Okay, let's look at h of z multiplied by h of z inverse. Look at h of z multiplied by h of z inverse. Then that yields, let's say over here, we're going to have 1 minus bz inverse into, now there is a special way of doing it, 1 minus bz upon 1 minus az inverse upon 1 minus az. Now to have the same magnitude response, what must you do? You must pick one of the numerator elements and one of the denominator elements. So how many can we have? You can choose 1 minus bz inverse by 1 minus az inverse, 1 minus bz upon 1 minus az, 1 minus bz inverse upon 1 minus az, and 1 minus bz upon 1 minus az inverse. All of them will have the same magnitude response. You don't believe me? I did both operations. Let's do a single operation. So I chose originally, I think I chose 1 minus 3z inverse upon 1 minus 0.5z inverse. Okay, so 1 minus 3z inverse by 1 minus 0.5z inverse has this kind of system. Now the claim is, have a look at this, 1 minus 3z upon 1 minus 0.5z inverse. Okay, now we have introduced a z, and we know that whenever you have poles and zeros at the at 0 and infinity, we don't care about them. So I'm going to add an extra delay. You know the delays don't have magnitude responses. So I'm going to write this as z inverse minus 3 by 1 minus 0.5 z inverse. Now this is equal to minus 3 times, okay, I'll write it in the, this is actually minus 3 plus z inverse by 1 minus half z inverse. Okay, so let's go back over here. So minus 3 plus z inverse, let's see what happens. Instead of 1 minus 0.3, minus 3 comma 1. Let's see what happens if I swap this. The magnitude response does not change. The magnitude response did not change at all. If you don't believe me, originally it was 1 minus 0.3, have a it moves, but keep looking at this again, it comes back. The magnitude response doesn't change. So in this particular case, there are actually 4 different realizations of the system that have the same magnitude response. Okay, naturally their phase responses vary. You saw that the phase response over here is different. The phase response, if I do minus 3 comma 1, is again different. It's different. So for all of those, the phase responses are definitely going to be different. Now for some cases, the stability means that you're going to have the non-causal solution to be stable, and those kinds of issues will start occurring, but that's still part of the game. So you can have multiple DTFTs which have the same magnitude, sorry, multiple Z transforms that have the same magnitude response. Now there is one important thing that you must note. What is the transformation you're doing for going from here to here? Okay, that is, if you want 1 minus 3 Z inverse by 1 minus 0.5 Z inverse. Okay, so now if you consider a system LCCDE like this, yn is equal to xn minus 0.2 xn minus 1. This is a simple LCCDE. And let's say that you have access to yn and you want xn back. Now, of course, you can try to do some equation manipulations and everything like that. But a simpler way would be to take the Z transform of this LTI system, Z multiplied by 1 minus 0.2 Z inverse. And if you want x of z back, you can just let x of z upon y of z would be 1 by 1 minus 0.2 Z inverse. Okay? Okay, and to realize this, we need to give something like this. This is the causal realization, which is causal and stable, and this will essentially give us the inverse system. So if you get yn, you pass it through this system, you will get xn back. Of course, this is a very simplistic picture, because in general you'll have to deal with other problems such as noise and how noise affects your performance. All these things have to be figured out. So this becomes an issue. That is something which you need to consider. But this kind of inverse systems exist in many situations. This is very useful in, for example, if you notice that whenever you take a picture with your camera, sometimes there's an initial blur and then your image is processed so that it removes the blur. Why? The blur is essentially viewed as a convolution, and then your phone or what a camera can figure out an inverse filter which will fix it for you. Whenever there is things like noise and all those things, then design and use of inverse filters becomes very challenging. That is something to keep in mind. So fine, this is an inverse system, okay, and we know that this 1 minus 0.2 Z inverse exists. Great. How about yn is equal to xn plus xn plus minus 1. Now in this case, something interesting happens. Okay, let us say that I do the same thing and I find that my x of z upon y of z is equal to 1 by 1 plus z inverse. Now this is actually a very difficult situation for us to deal with, because the z mod z equal to 1, the unit circle can never be within the ROC. So you cannot have a stable way to realize this. In fact, there's no stable way to realize this. I'll give you an example of what this indicates. Let's say that you give your xn is actually 1 minus 1, 1 minus 1, 1 minus 1, etc. what will your yn be? Your yl will in fact be 0, right? If you look at it, the yn will in fact be 0. If your yn is 0, that means that there's no way to recover xn, right? So this particular filter has a null at z is equal to e power j pi, that is at omega equal to pi, null. Okay, you don't believe me? This filter is 1 1. Notice that the magnitude response goes to 0 at pi, which means that this filter has a major issue in that it is not invertible. In fact, even if you guarantee that the omega equal to pi filter doesn't exist, the inverse filter is actually not stable, which means there can be some inputs which can lead to, or even some noise samples can cause it to blow up. So this means that inverse filters may not be realizable in several situations because of this kind of issues. So now, because of these issues, how do we handle this situation where we have inverse filter? We need to have the inverse filter. Rather, when can you guarantee that inverse filters do exist? So for this, I'm going to give you a special type of system called minimum phase system. Okay, so a minimum phase system actually indicates something special. A minimum phase system has its phase response all bounded to be within minus pi and does not have any jumps. And there is a lot of equivalent definitions. I'll give you one of them. All poles and zeros lie within the unit circle. Now this is actually very important. Let's take an example. 1 minus 0.2 z inverse upon 1 minus 0.3 z inverse. Okay, mod z is greater than 0.3. This satisfies that all the poles and zeros lie within the unit circle. Okay, now this satisfies the fact that all the poles and zeros lie within unit circle. And what about the inverse system? 1 minus 0.3 z inverse by 1 minus 0.2 z inverse, mod z greater than 0.2. This means you have a causal and stable inverse. So what does this mean? Whenever you guarantee that all the poles and zeros of a system lie within the unit circle, then you have a stable and causal inverse. And this has a connection with minimum phase. What is it? So let's look at this. I think it was minus 0.2, 1 comma minus 0.3. We'll update it. If you look at the phase response, notice that the phase response doesn't have any jumps. It doesn't have any jumps of pi or anything like that. What are jumps of pi? Jumps of pi correspond to sign changes. Sign change means that the magnitude response goes to 0. A magnitude response going to 0 indicates that, so because I'll give you an example of thinking about it. Okay, whenever you have a case where there's a jump of pi or jump of 2 pi and things like that, that means that the phase response changes significantly. Of course, now you can always say that I'm going to add some delays and let's say I'll add 20 and then if you look at it, then you're going to have this kind of jumps of 2 pi. But you won't ever have jumps of pi because of the sign changing. A jump of pi occurs in a phase response only when the sign changes, SIGN sign changes. In the case of a minimum phase system, if you geometrically see, the angles never exceed that pi. The angles are never going to exceed pi. Let's take another example. Let's take a simpler example. Let's take 1 minus 0.2 z inverse into 1 minus 0.9 z inverse. Of course, in this case, you can have the whole z as ROC. Inverse system is going to be 1 by 1 minus 0.2 z inverse, 1 by 1 minus 0.9 z inverse. And I'm going to say mod z greater than 1, causal, stable, inverse. Okay, don't believe me. Let's actually evaluate what this works out to. 1 minus 0.2 z inverse plus 1 minus 0.9 z inverse, 1 minus 1.1 z inverse plus, okay, 1 minus 1.1, 0.18. So 1 minus 1.1, 0.18. Okay. Again, notice that the phase response does not leave. Phase response does not have any jumps. It does not leave this minus pi to pi range. There is a pole at of course it's a 0 at 0 that we'll ignore. There's a pole at 0.2, pole at 0.9, and this is exactly what happens. So now, what are we able to say? Notice that this minus 20 and crosses 0 at around 0.4 pi. If you look at the inverse system, notice that it's just going to be a mirror image. It's just going to be a mirror image. Oh, notice. There is an extra scaling, but it's just a mirror image. It actually worked out. And this phase response is just the negative. I'll go back to the original system, have a look. So this is just a mirror image with a shift. Okay, so there's actually nothing to, in the sense, of course, the magnitude response is going to, when I say mirror image, I mean both of them will add up to 0. That's exactly what is happening. You start at around minus 20, go up to somewhere around 7 or 8. Let's see what happens when I do this. Okay. You don't do the same thing, but the reason is because of the scaling. Okay, there's an extra scaling factor which I have to handle that I have not handled. The pole 0 plus doesn't handle, but the phase response definitely shows the negative. Okay, so this is indeed what is happening. Okay, this is what you should observe when you talk about the magnitude and phase responses. So I will try, maybe just to prove it to you, I'll add a peak over here to 1. Okay, 1 minus 0.1, 0.18, and this I will make okay. So yeah, you see that this little tiny blip is there, right? So that blip was there even in the other. They add up to 0. That is exactly what is happening. So now, whenever you have this kind of situation where you have a minimum phase system, a minimum phase system always has a causal and stable inverse. And in fact, the inverse, if you notice, this case is also minimum phase. So now, there's a key realization. Every h of z can be decomposed as h of z is equal to h min multiplied by h ap of z, where this is minimum phase and this is all pass. Now this should not be too surprising to you if you remember what we saw just some minutes ago, because whenever you have, remember, you know that you can get the same magnitude response by flipping around these poles and zeros. For example, if you look at 1 minus 1 by 3 z inverse by 1 minus half z inverse, okay, this is already minimum phase, but we'll take something else. Let's say we have 1 minus 3 z inverse. Okay, this is definitely not minimum phase because it has a 0 at 3. So if you look at the inverse system, you will not have a causal stable inverse. In fact, the stable inverse will not be causal. The causal inverse will not be stable. So if you want to now express this, notice that I can express this as a minimum phase system by just doing this small change. What do I need to do? I need to basically be able to write this as, so there is since there is a 0 at 3, what I'm going to do is I'm going to basically consider the all pass system that has a 0 at the pole at 3. Okay, so I think I'll be very careful. So I'm going to write this as 1 minus. Okay, let me just do the manipulations and you will see. This 3 into 1 minus. Sorry. going to be 3 into, so okay, maybe I will just write do it in a more simple manner. So I'm going to basically write this as 1 minus 3 z inverse divided by z inverse minus 3, okay, into z inverse minus 3 by 1 minus half z inverse. Okay, so now notice that this particular part 1 minus 3 z inverse by z inverse minus 3 is actually an all pass filter. Why? You can directly inspect the flipping of the coefficients, but even otherwise you can sort of see that if you notice that this has a pole, this has a pole at 1/3, this has a 0 at 3. So this is definitely an all pass filter. If you want to exactly get into the same form, you can also write this in terms of something like z inverse minus 1/3 by 1 minus 1/3 z inverse. Okay, so that is just by doing some minor manipulation you can get this form. Okay, so if you want to do that you can even do that, but I'll leave it in this form. Now if you look at this particular part, this 0 is at 1/3 and this pole is at half. So this is an all pass filter, the minimum phase filter. Now how did I get this? To get this, if you recall, we said that we could always find equivalent magnitude responses, right? By flipping around the zeros and poles. We did that. The same way you can do it. And I told you that this flipping around zeros and poles is going to give you, flipping around zeros and poles is going to give you this transformation using an all pass filter. So similarly, if you just look at some other example, let's say we take let's say we take 1 minus let's say 1 minus 2 z inverse into 1 minus 4 z inverse. This is easy. There are two zeros, one is at 2, one is at 4. So if I expand, I'll get 1 minus I think 6 z inverse plus 8 z power minus 2. This is basically the system. Naturally, you don't have a stable causal inverse and all those problems occur. But can we write this as an all pass multiplied by a minimum phase? Again, notice that when you have 1 minus 2 z inverse, okay, 1 minus 2 z inverse divided by z inverse minus 2 into z inverse minus 2, okay, multiplied by 1 minus 4 z inverse divided by z inverse minus 4 multiplied by z inverse minus 4. So now if I group them as 1 minus 2 z inverse by z inverse minus 2 into 1 minus 4 z inverse by z inverse minus 4 and into, if I do z inverse minus 2 z inverse minus 4. Now z inverse minus 2 has a 0 at half, z inverse minus 4 has a 0 at 1/4. 1 minus 2 z inverse by z inverse minus 2 into 1 minus 4 z inverse by z inverse minus 4